Okay. Hello. Thank you for this opportunity to present. So the work I want to talk about today is a couple of methods we've looked at for treating different timescales in weakly coupled variational data assimilation. So this is work being done with Nichols at the University of Reading, but also with some contributions on part of it, on a certain half of it, which I'll mention, from Sian Leung and from Sheridan Shathir, who were working as postdocs here previously. So an introduction to this, we know that the ocean has slower timescales than the atmosphere. And so in ocean DA, we normally use longer time windows in the atmospheric DA when we're doing things separately. So standardly in atmospheric DA, we have time windows of say 6 to 12 hours for global scale data assimilation. But in the ocean, it's often of the order of several days. But the question is, how do we bring these things together when we're doing coupled data assimilation systems? Because we need to find a way often of using a common time window within the coupled data assimilation window, a common assimilation time window. And because of the fast growing areas in the atmosphere, this common time window often needs to be shortened. So the Met Office, for example, in their coupled data assimilation, they use a time window of 6 hours, which corresponds to the atmospheric timescales, because that corresponds to the fastest growing areas in the system. But this means, first of all, that the common short time window means that the oceanic state has less time to respond to the observations, and so can respond less flexibly. And there are also with issues with the cutoff time, that ocean observations may take longer to come in. So what we've been looking at is two proposed solutions here. One is what we're going to call the smoother method, which we partly presented some of this at the in-person ISDA in Colorado. That should be, I think, not 2024, that should be 2023. But also a new method we've also developed based on a weak constraint 4D bar. So in this talk, I'm going to present these two methods in part one and compare these two methods in a simple idealized model. And then I'll speak briefly in the second part about, on the smoother method, we've developed another slightly more complex idealized model and done some further tests of this method. So first, what is this smoother method? Well, the idea of the smoother method is to add an extra step in the assimilation to adjust the ocean state over a longer window. So if we consider, for example, we have some short time windows, say this T is 6 hours, so this is from 0 to 6, 6 to 12, and so on. We may think about doing our normal weakly coupled data assimilation. So in the weakly coupled variational data assimilation, I mean where we're getting, by weakly coupled here, sometimes called quasi-strongly coupled, I mean that the background state and the innovations are coming from the coupled model, but we're running separate inner loops for the atmosphere and the ocean. And so what we can do here is we can use this weakly coupled system with the separate outer and inner loops for the ocean, separate inner loops for the atmosphere and the ocean, to cycle through our normal cycle of coupled 4D bar, say for example in 4 6-hour chunks. And then what we can do is we take the analyses from here, the ocean analyses, and we recalculate the innovations of the ocean with respect to the analyses we produced. And then we do a minimization of just the ocean cost function over the whole time window. Now, we're only using these ocean analyses to calculate the innovations and the background. So essentially, it's like introducing a first guess. So there's no problem in introducing correlations of using the observations twice. But we do this smoother step over the whole window where we're using these analyses and getting a better fit to the ocean observations over the whole time window. The second method is based on the weak constraint method, and what we're going to do here is to treat the whole problem over the long time window, but by doing a weak constraint problem in the atmosphere and a strong constraint problem in the ocean, because we're seeing that this window we're over the timescales where the ocean is still quasi-linear. So we'll still have the same outer loop, but in the outer loop run of the coupled model to get the innovations. But then when we do the inner loop cost functions, for the ocean, we'll have the standard inner loop cost function over the whole window. For the atmosphere, we will run, because we know we can't minimize the atmosphere over so long a window because of nonlinearities, we will have treat the atmosphere as a weak constraint and run a weak constraint inner loop cost function in the atmosphere. So I'm going to test these methods on an idealized model. This model is a very simple model where we have 5 equations. The atmosphere, or the faster variables, are the 3-variable Lorentz system, the Lorentz 63 system. Whereas for the ocean, we have these 2 variables, W and V, which is essentially a linear oscillator forced by the atmosphere variables. And we have some forcing back from the ocean into the atmosphere, based on this alpha parameter. And so what we've done is implemented this 4D-var, weakly coupled 4D-var system based on the incremental version, where in the inner loop cost functions, we use both 4D-var for the atmosphere and the ocean. In practice, often people would use, at least we have in the Met Office, they use maybe 4D-var in the atmosphere and 3DF-GAT in the ocean. But for the purposes of these tests, we're using 4D-var in both. Looking at just the model properties, this is an ensemble of the model systems over 3 time units for the atmosphere variables on the right and the ocean variables on the left. And what we see is after about 1.7 time units or something, things begin to get very chaotic. And so what we've done in order to test these methods is we're going to test over 2 long time windows. So for the whole period of 1.5 time units and also 3 time units, where 3 time units were definitely in a very chaotic regime. So we're going to use these 2 cases, the short time windows. So the short time window is based on that previous ensemble. We're going to have 3 short windows of 0.5 time units. And so then when we do either the smoother over the long window or we do the weak constraint over the whole window, this is over a window of 1.5 time units. With the weak constraint model error for the weak constraint system, the atmosphere model error specified at the end of each short window every half a time unit. Instead, for the long time windows, we're going to consider over the whole period I just showed on the ensembles of 3 time units. So we'll have 3 short windows of 1 time unit each. And again, the smoother window will be over 3 time units. Or when we do the weak constraint, we'll have the model error at the end of each short window, so every 1 time unit. I'm just going to show a selection of experiments because of the limited time. But so the ones I'm going to show, we've got background error variances of 0.1 in the atmosphere and 1 in the ocean, and the observation variances are 1/10 of these. So first case 1 for the short window, what I'm showing here on the left, well, if we go from top to bottom, we have the atmosphere variables X, Y, and Z, and on the bottom, the ocean variables W and V. The left is the standard weakly coupled system, the middle is with the smoother method, and the right is with the weak constraint method. So what we see here, and what I've done, I should have said, we have atmosphere observations indicated in blue at the end each 0.5 time units, and we have ocean observations instead just at the end at 1.5 time units. So when we're running the standard weakly coupled system, of course, in the ocean, because we don't have any ocean observations in the first time window, the only update to the ocean is coming through an update to the analysis to the atmospheric analysis when we run the coupled model. Well, then we see in the final window, we do see some improvement and fitting to the, starting to fit to the observations. When we look at the weakly coupled, the smoother system, the atmosphere is very similar. Well, it's always the same by definition. If we're just doing one window, we'll look at some cycling experiments later. The ocean, in this case, is very similar to the weakly coupled, but we do get a slight improvement to these variables, and I'll show the actual values later. And because we're doing this smoother over the whole window, we can get a slight improvement, not just in this final short window, but over the whole period. When we look at the weak constraint method in this, we find, again, now because we're fitting a trajectory over the whole period, we find we do get an improvement over the whole period. And of course, we now have one continuous trajectory over the whole period. What's more interesting is when we look at the longer window, where we're in a very, I should have said here that the red is the analysis and the black is the truth. Sorry, I hope that was clear. It's from here. But it's becoming more important where we look here when we do over the 3 time windows, where the weakly coupled system, after the first time window, because we have no observations of the ocean in the first time window, when we get into the second short time window, here we're in a very chaotic regime. And because we're using these short windows of 1 time unit now, and the weakly coupled system really goes off track and never recovers. So the standard system never recovers. And even the atmosphere fields go off track, fed in by the ocean. When we do this smoother system, so this is the middle plots, we're using this observation to fit in the final window, but also to smooth over the whole period. And so we do get an improvement over the whole period with respect to the weakly coupled system, particular improvement in the final window, but also we see an improvement with respect to the weakly coupled system in this middle period as well, with perhaps a slight degradation here. When we look at the weak constraint case, now because the weak constraint is designed to go over a full time window, over a longer time window, even when it's chaotic, because we're allowing for the model error in the atmosphere, and then therefore allowing for the possibility of more nonlinearities, we do get, in this case, a much better fit, and we manage to fit the ocean variables and the atmospheric variables very well by using this weak constraint approach. Remember, weak constraint in the atmosphere, strong constraint in the ocean, but fitting everything over the whole window, the whole 3 time unit window altogether. So in this case, with a longer window, the weak constraint really works best. When we look at the actual error norms, so here I'm showing the initial error for the first case, the initial error norm for the total norm and just the atmosphere and the ocean. So this is the norm with respect to the truth. The initial and final norms from the standard weakly coupled scheme, the smoother and the weak constraint. In the case of the initial norms, both of the smooth and the weak constraint really improve with respect to the standard experiment, with the weak constraint showing better. When we look to the final error norm, the smoother is still showing an improvement with respect to the standard, but the weak constraint is showing a slight degradation. And this is what we would slightly expect in the weak constraint, because we're really fitting the initial errors, the initial state and the model errors throughout in order to try and fit the observations. So we see just a slight degradation at the final time. However, when we look at case 2, which is of course the more chaotic one over the whole window, here we see that with the weak constraint shows a lot more improvement both at the initial time and the final time. So at the initial time, the weak constraint here is showing a big improvement over the initial error norm. The smoother shows a slight degradation, and this is because the smoother, of course, is just using the output from the standard scheme and then doing the smoothing. So if the standard scheme is not performing very well, then or if the standard scheme goes completely away from the truth, then the smoother is not enough to get that back. However, we do see once we get to the end of the window, because we've got the observation there in the ocean, that the smoother and the weak constraint are both showing a big improvement with respect to the final error norm. And so with the smoother in this case being slightly better for the total and the atmosphere norm, but the weak constraint better for the ocean. So in summary of this part one, both the smoother and the weak constraint method give an improvement over the standard weakly coupled method. The weak constraint tends to give more improvement at the initial time, but it can make things worse at the final time for short windows, whereas the smoother can make things a bit worse at the initial time in order to fit the final time better where we have the observations. Now, of course, I've not tried with different the sensitivity if we had observations earlier in the window, for example, as well. What we've not done here is do the sensitivity to different parameter choices. For example, in the weak constraint case, we need to specify the model error Q. I just did it as a scalar multiple of the identity here, and in this case, we've not shown any cycling and how that works. The other point to make here is that possibly the weak constraint method, because we're just doing the one minimization, could be potentially cheaper than the smoother method, but that's something we need to look into a bit more. So that's all we've done in the comparison of both methods. Since then, what we've done, and a little bit of the smoother method I presented last year at ISDA, we've done since then developed a new model to develop further examination of the smoother method, but not yet the weak constraint method. So this is we wanted a slightly more complex, idealized model, which was less chaotic or less sensitive to very small perturbations, but still chaotic. So I've adapted this method from Lawrence 2005. It's a 2 timescale model where X is in the atmosphere and Y is in the ocean variables. Now in the Lawrence paper, this was presented as a model. Lawrence in this paper was trying to do a model where the fast scales, or say the slow scales, were an average of the fast scales, for example, in convective systems. And so he didn't develop these equations further, but we want the fast and slow scales to be independent because they're representing the atmosphere and the ocean. So we've developed this a little bit further, this method. So we now have a forcing of this by this gamma parameter of the ocean forcing the atmosphere and the atmosphere forcing the ocean, with this alpha parameter that allows us to change the different timescales. And with these choice of F parameters, both of these systems are chaotic. And if we look at the error growth in these, so this is a plot of the error growth against time step, the atmosphere error growth is approximately 4 times the ocean error growth. So we have the right kind of split in timescales. If we assume in the atmosphere that the doubling time of an error is around 48 hours, this would correspond to the ocean doubling time of around 8 days. So we're more or less in the right kind of range for the split between the atmosphere and the ocean timescales. And if we assume the atmosphere doubling time is 48 hours, then this means that one time step in this model corresponds to 3 hours. So what we've done is we've done an experimental design of a short time window, where the short time window is 4 steps of 12 hours, but then every 16 steps or 48 hours, we do this smoothing procedure. So to run the model, we spun up the model for 5,000 time steps to make sure we're on the attractor, and then we've run cycle data assimilation experiments for 50 long windows. So the background errors are chosen to be these values in the standard deviation, 0.5 and 0.8, which were calculated to be more or less 10% of the variability of the model, and we've used a second order autoregressive matrix for the correlations. The experiments I'm going to show, we're going to observe the atmosphere at the end of each short window and the ocean at the end of each long window every 2 spatial grid points. And we're going to run for 50 cycles, so 50 cycles of long windows, and then take the average error norm over the 50 cycles. We do need to think about how do we do the cycling, because once we do the smoother step, so we run our normal weekly coupled system and then we do the smoother step, and that gives us an ocean, new ocean step at the new ocean state at the initial time. How do we combine that with the atmosphere to then run and cycle? Now we've tried different things. What we do is we take this new ocean state and the atmosphere state we analysed here, run forward to the next short window, and at the end of each of these short windows, we reset the atmosphere to the atmospheric analysis that came from the short window assimilations. And so that ensures that we're making use of the atmosphere observations and information we used in the short window cycles. And so we reset the atmosphere states, and then once we get to the end, we run and do the next cycle. We have tried other cycling methods and they do show similar results. I don't have time to discuss them now. So this on the left is showing the weekly coupled system, and on the right the smoother system, where we have the error norm of the total error norm, the atmosphere error norm and the ocean error norm from top to bottom, where blue is the background and red is the analysis. And these are average, so we're doing windows, long windows from 0 to 0. So we do 4 short windows of time 0.05, and every 0.2 time units we then do the smoother step and then cycle. And this is the average over all cycles. So what we see is simply, first, if we just compare the scales with in the ocean, we have a big improvement in the ocean with this smoother compared to the standard weekly coupled when we cycle over the whole pit. And the improvement is not just in the final window, but is over the whole window because we're doing this smoother step, even though we only have observations at the final time. But also importantly, because we're cycling, the ocean improvements from one cycle can feed into the atmosphere, into the coupled simulation to the next cycle to calculate the innovations in the background. And so we also then feed into the improving the atmosphere, and we see an improvement, a small improvement in the atmosphere when we're cycling over the 50 cycles. Small but significant improvement. So doing this smoother is also feeding into the atmosphere. We've also tried, of course, we'd expect this to depend on the smoother because it's only using ocean observations to depend on how many ocean observations we have. So we've also looked at when we have sparse ocean observations in time, in space, where this is now every 10 grid points up to the size of 40 rather than every 2. And what we see is, of course, the improvement now we wouldn't expect to be as good, but still with very sparse observations, the smoother is still giving an improvement over the standard weekly coupled scheme. And we're still seeing an improvement, that improvement feeding into the atmosphere as well. One important aspect of this is that we can, when we do the smoother step, we can actually use this to incorporate later arriving observations. So what we can think about is, suppose we're doing this weekly coupled system running through these short windows, but by the time we get to the end here, a new observation has arrived at time t equals 0.1. Instead of running the whole weekly coupled system together, again, we can incorporate that observation just into the smoother step. And that's what we're doing here. So on the left, I have the weekly coupled system just without the observations at time equals 0.1. In the middle is the weekly coupled system if that observation hadn't arrived late, if we had it at time 0.1. And on the right is where we've done the weekly coupled system as on the left, and then applied the smoother, but adding this extra observation into the smoother step at time 0.1. And you can see that we can do, not only are we making an improvement here in the ocean with respect to the standard weekly coupled, but we do have a bit of an improvement even with respect to the fact of if we had that had that extra observation there in the first place, which is the center plot here, because we're using, of course, now in the smoother step, we're using the observations at point 1 and point 2 over the whole window to try to correct the whole window, and so we even get a correction at the initial time, which we were not able to do in the weekly coupled system. So to summarize part 2, the smoother method has been further investigated in a new coupled model that we've developed, and now with cycling. We've seen a benefit in both the ocean and the atmosphere, even with sparse ocean observations, and we can use this method to incorporate late arriving observations. And we're currently preparing a paper on this part of the work. I should have said this part 2 is the work where Stian Lung and Sheridan Chateau were also involved in doing some of these experiments and setting up the system. So, to conclude, we've developed 2 new methods to deal with different timescales in the coupled data assimilation. One is this smoother method, which runs several short windows as a standard weekly coupled data assimilation, and then does a correction step to the ocean over a longer window using the analyses from the standard weekly coupled data assimilation. The other method is a weak constraint method, where we're going to minimize over a longer window according to the ocean timescales, but treat the atmosphere as a weak constraint over that period, so that we're able to fit the atmosphere observations and the ocean observations simultaneously within the 2 inner loop cost functions over the whole period, instead of doing short windows. In the first idealized model I showed, both methods showed some benefit. It's clear that in some cases one works better, in some cases another works better. I think partly because of the way these methods are designed, but that's probably something we need to look at slightly more closely. We have developed, and I showed in part 2, the smoother method. We've further investigated it in this new coupled Lorentz 96 model, and it's showing promising results even when we're cycling. And so the next steps we want to do is to further investigate also the weak constraint method in this new Lorentz 96 model with some cycling, and compare the results with the smoother method and the standard weak constraint. So, and I'll stop there. Thank you. Thank you.
Thank you very much, Amos. That was really nice to hear. Yeah, I think I've heard parts of that before, and every time I hear it, I sort of realize the similarities with the operational systems, and it should be really interesting to look at how we can compare operational systems with these methods. So I am going to, first of all, encourage everyone who has a question to go to the OPAD and put it in, follow Lawless's his questions and add them in after that. But I'm going to take the opportunity to have one question first, if that's all right. So in part 1, when you were using the Lorentz 63 system, I was sort of wondering, are the nonlinearities which you have in the ocean there really representative? Because over one sort of atmospheric time step, you could see this ocean part diverging really quite a lot. So were you as sort of careful as you were in part 2 with the timescale choices there?
I think on the first one, we mainly used the timescale choices based on the difference between the we did look at the timescales. I'm trying to remember. So we did have a brief look at the difference in the timescales of the error growth, and showed that there were different timescales, but perhaps not. I don't have the plot for that. I think we were also looking at these kind of ensemble plots.
Yeah.
That probably doesn't say about the error growth. But sorry, so that's not the right plot. But we did have a look at the plots to make sure that there were the right kind of split between the atmosphere and the ocean.
Well, I think once you've moved on to the part 2, it's everything's answered in there anyway. So that's really good. So I'm going to go to the OPAD and see what questions we got. So the first one's from Lars Nerger. He says, obviously, thank you, Amos, for the very interesting talk. And do you cycle the smoother? I run from the smoother solutions.
Yes. So what we do, and I think, I don't know whether I. So what we do when we take the smoother here, so this is what I was trying to. There's different ways of doing it. So we take the smooth ocean solution, and we take the non-smooth because we just have the standard atmosphere solution here. We run the coupled model from that solution, and then we have the old atmosphere analysis here. So we reset the analysis, but keeping the ocean state from this coupled model run, and we step forward like that. So we're using. So then by the time we get to here that we're cycled, we've run the coupled. We have run the coupled model starting from this smooth solution, but with a nudging in these atmospheric analyses, so to speak, and that's what we're then cycling with to run to the next background.
I see. Thanks. So we have another question from Andre from Barcelona Supercomputing Center. So he's taken it a bit away from atmosphere and ocean and into atmospheric chemistry. So would it be possible to extend this coupled system of ocean and atmosphere dynamics to atmospheric chemistry with an extra smoother assimilation time window? So thinking about tracers with reactions of with sort of hourly timescales. So to add, I think adding an extra loop onto this.
I think so. I'm not sure whether it'd be an extra loop or replacing the ocean one with a. Oh, I think doing. Good question. I think you would need thinking about. I mean, I think therefore, I mean, it depends whether you're then talking about still doing a 2 timescale system where you've just got the atmosphere and the chemistry, or whether you're thinking about a 3 timescale system, the ocean, the atmosphere, and the chemistry. I think if you're doing that, then it would need adding an extra smoother loop. I think it would be possible. So to have in the small window, smaller timescale things with a smoother over the short time window, it would be possible. We would need testing as to how well that would work.
Yeah, I agree. I think it's a flexible enough concept that you can make it work for your application, right? So we have one more question. So from Zifeng Yang. So how much the smoother and weak constraint depend on the length of the time window? Yeah, so how does the performance depend on the choice of time window?
I mean, clearly it will depend, and particularly we saw that I think in the first part where we have the short time window, the weak constraint was better at the small, at the start, the smoother better at the end. But when we got to the longer window, the weak constraint was showing better. I think if we think about the way they work, using the weak constraint, I mean, the ocean assimilation is, so we probably don't want the longer window longer than the standard ocean assimilation. You want to assume that the ocean is fairly linear over the long window in order for the smoother method to work, because you're doing a minimization of the ocean over that window. And if you want to treat, whereas with the weak constraint method, in a sense, you don't have to assume anything about the atmosphere. You're just assuming it's fairly linear as the weak constraint over the shorter windows. Now, if you wanted to extend this, I suppose you could also think about putting a weak constraint in the ocean and making the window even longer. But I think this depends. So I'd say the smoother depends on the ocean linearity length. The weak constraint, the ocean part, if we consider just one minimization, depends also on the ocean linearity, whereas the weak constraint atmosphere parts depends on those sub windows depend on the atmospheric linearity part.
Okay, that's great. So with that, thank you very much, Amos. And I'm sure if there are any more questions, they can go into the